Hello, everyone. My name is Stolz. I am CTO with Photoneo. My presentation is basically an invitation to our booth, Hall 10, C40. The show is not over, so when I'm finished, please come over and take a look at the demos. I'm going to talk about our recent developments. We are a 3D vision company that provides 3D sensors and robotic intelligence, and this time we are extending our portfolio in a direction of previously not really easy solvable use cases that are maybe better demonstrated here at this picture. There are many situations in which objects are not really well scannable. Previously, we were basically struggling with these types of objects. And also there are use cases in our domain where single perspective is not enough, where a camera or a system need to basically look behind in order to understand the geometrical composition of the scene. But before I start, I would like to introduce Photoneo a little bit. We are a company based in Slovakia, Central Europe. We are over 300 employees currently. We have about 45 and more distributors and integrators around the world. We currently have more than 8,000 solutions deployed. And what we are actually doing is probably illustrated very well in these little videos. We are a leader in vision-guided automation because we have the most industry-proven beam picking installation, most major and industry-proven installation in the world. These are a few of our partners and customers. Our portfolio is based on 3 pillars. It is a 3D sensor hardware, basically sensor components. Then we have beam picking software solutions where also AI is being massively used lately. And then we have a digital twinning software that is now well and nicely integrated into the beam picking software in order to bring some advantage and capabilities over the previous solutions. One of our key components in our solutions is a camera called MotionCam 3D, MotionCam 3D Color, to also paired with a color camera, that is occupying one very interesting gap in a current 3D sensor portfolio of our competitors. On one hand side, there are traditional methods like sequential structured light approaches that are extremely good, extremely high quality, but it takes time until you get to all the data that is needed for capturing a 3D scene. So they are very good for demanding application, but they are not very fast. So static scenes are needed for sequential structured light approaches. On the other side, there are simple applications that require dynamics. So for example, some simple robotic handling is typically tackled by time of flight or active stereo. These methods are let's say, simple or easy to deploy, but they provide much lower quality compared to structured light. And then there is this quadrant in which our camera is located with a technology called parallel structured light. I'm not going to dive into this technology here, but if you are more interested, we can discuss. It's based on a proprietary 3D CMOS image sensor that was invented and developed by Photoneo. We received a major Vision Award in 2018 for this sensor. And that makes really the difference that 3D data, high quality 3D data can be captured in a certain pace without waiting in a snapshot. So what does it really mean? Just to give you an idea, we used to say that we basically, with our MotionCam 3D, we have solved the problems of 3D vision. On a left-hand side, you see a scene that is moving. It's not necessary that it's moving, but in many circumstances, you cannot avoid motion. You cannot, for example, avoid vibrations. many of these effects and things influence the way the point cloud or the data is generated. So basically, if such situation happens, one may want to apply time-of-flight camera, but actually from time-of-flight camera, you get pretty fast and low latency response, but the point cloud quality is not really great. On the other side, if one wanted to have more points, better quality, maybe a structured light approach, then the structured light approach would be maybe applied, but actually whenever there is motion, there are artifacts, there are severe distortions of the point cloud present, while our MotionCam 3D is capable of capturing high-quality point cloud in motion without any distortions based on or that would be affected by the non-stationary property of the scene. Now, high quality, high resolution, what does it exactly mean? In our MotionCam, we can deliver 2 million points, 2 megapixels, 2 million of high-quality 3D points without any distortion by motion. Again, motion is not really needed. You can use it as a standard 3D sensor, but if there is a motion, there is no problem with that. Compass, very briefly, is our core technology behind our MotionCam. It's a proprietary CMOS sensor developed by Photoneo, and just on a popular science level, it is as if the camera was capturing multiple images at the same time. So there is a technology called mosaic shutter implemented. It's not a rolling shutter, it's not a global shutter, it's something different. Photoneo has this technology patented. We have full control over how it is used, and we are exploiting this vast flexibility that this approach gives us to be able to do standard 3D sensing, but recently we extended also to other use cases. Here I would like to briefly give you an idea. On the left-hand side, there is an image captured, or images captured in a sequence with a standard structured light camera. Imagine there is a process, an object is dropping on a table. It's a ping pong ball that is dropping on a table, and a standard structured light camera would project multiple patterns, one after another, and the ball would be dropping. So basically, each pattern would hit it in a different time instance, while our MotionCam and Compass can capture it all at the same time without any motion blur or any deviation between the frames. Obviously, this has an impact on the 3D point cloud. 3D point cloud is massively distorted if there is a discrepancy between patterns captured over time, while with Compass and parallel structured light, one gets a clear, crisp, high-quality point cloud, even though the object is moving, because it is an area scanning snapshot system. Here are a few technical details. With a standard global shutter sensor and a standard projection technology, a camera is observing a scene over a time window, while the projector is creating a pattern via modulation of the light. This is standard. One cannot really parallelize this process. One cannot really project multiple patterns at the same time. While with our proprietary CMOS sensor, we are able to exchange the roles of the projector and the camera, and the modulation is actually in our pixels on our sensor. And we can produce these patterns in parallel. An example of the point cloud, again, and the data that is being produced by our MotionCam 3D. There is an obviously very fast process happening in front of the camera. We can capture it in a very fast pace. and deliver depth, texture, even surface normals that are calculated within the camera, and obviously a 3D point cloud. Now coming back to the topic of my talk, now you know what the motion cam can do or used to be able to do. Recently, we have introduced new modulation strategies that are able to cope also with nowadays very common challenges in a logistic context, picking of transparent, translucent objects, different types of wrapping material, or in a medical domain and pharma domain, various types of syringes and vials packed in plastic covers. In order to do this, we have introduced a pattern, a special proprietary light codes that are interacting with the scene quite different. They are able to basically differentiate between multiple layers that are on or produced by the transparent object, so that we can actually read response from the first layer, second layer, third layer, and so on, and basically carve out the surface that is the nearest. As you can see here in the video, our previous generation of the cameras was not really capable of capturing all these types of SKUs that you may find in the warehouse. Now we have vastly increased the amount of objects that can be handled with a good success rate. Here a few other examples how transparent objects can look like. We have also introduced algorithms for nice filling in gaps in the data, because for certain applications, kind of hollow point cloud is not really great. For AI, it is good to have a complete point cloud. From time-of-flight cameras, people are used to get a complete point cloud. For this, we have introduced also some nice functions that can enrich quality of the point cloud that is produced by our sensors. All this is possible thanks to, or only by firmware update. We didn't have to really change the hardware for this. Additionally, these new coding strategies are also capable of improving readout of very complex objects. Here you have I would say, quite standard beam picking situation from automotive or whatever industry, and you see that there are metallic parts that are very complex because they reflect on each other. They are, if active light is sent to one part of the scene, it may reflect on the other part of the scene and produce a false readout, false artifact. With new coding strategies that we have introduced, again, just by firmware update, we are able to get much better quality point cloud and get much better understanding of the geometry of the scene. The same applies also to dark and glossy objects. With these new approaches and strategies, we are able to increase the amount of well-read and well-recovered pixels in the scene by really great amount. You know, I don't want to say the number, but it improved very dramatically. Last but not least, for the sensor itself, we have also introduced or brought a third generation of our ambient light suppression. That is thanks to the very, let's say, good and tight control of the sensor and also our laser projection unit. We are able to scan up to, in the ambient light, up to 100,000 lux, and we are able to basically capture dynamic range of many f-stops. So from very dark, there are deliberately some shadows on the scene that are basically creating very little ambient light or containing very little ambient light compared to the directly sun-illuminated regions in which there is lots of ambient light and you don't see any difference between these two areas. In the factories, this is extremely important. Now, this brings me very briefly to the second part of my talk. what to do if a single perspective is not enough. There are many, many use cases in which one needs to look from various perspectives in order to be able to see what's there, localize the part, and handle it appropriately. We have in our portfolio a software called Foxy 3D Instant Meshing, which offers, plurality of configurations where object is either, placed on a marker board or a rotary table or a robot or a gantry and observed from multiple perspectives. There is a C++ library one can integrate very, very easily into customer solution, but we have now leveraged this on a second level also in our bin picking software that seamlessly is now able to integrate multiple views from multiple sensors or a one hand-eye sensor that doesn't need to really stop between acquisitions, because with motion cam you can acquire in motion. Take those multiple views, integrate it into one comprehensive 3D model, and allow you to pick also parts like these L-shaped object here on the left-hand side. One can see, funny parts that are actually very hard to recognize and pick if it is observed from one perspective. If multiple views are merged together, it is much easier and more precise to identify these objects from such compound point cloud. This brings me to the conclusions. If light doesn't behave, we have brought plenty of improvements of our sensor technology thanks to our proprietary new light codes and the way we are controlling our sensor. And if the single perspective is not enough, now we have a very seamless and easy-to-use solution with our bin picking software that can now integrate multiple views from our camera in a better point cloud and better recognition rate. Thank you very much. You are most welcome in our booth if you are interested.
Thank you for this really interesting talk. Thank you very much. Any questions? We have time for 1 or 2 questions. Obviously not. I have a question, of course.
There was one.
Oh, there's one? Oh, I didn't see. Sorry.
I'm sorry.
One question regarding resolution and working distance. What is the minimum working distance and field of view what you can offer with your sensors?
I mean, from the principal point of view, there is no limitation. You can, for smaller working distances, one can shrink the baseline. Our system is a stereo system, so for every working distance, there needs to be an appropriate baseline. We have our standard portfolio. So if you have a specific application in mind, you can look into our offering, and there is like plenty of models from very short, from 30 centimeters up to 4.5, 5 meters distance. Small models are used for inspection purposes because it's down to 200 or 150 micrometer accuracy. Large baseline systems are used for logistic applications, obviously. But from the point of principle, one can design whatever system is appropriate.
Okay, one more question from my side. Yeah. Very interesting mosaic pattern. What you put on top or not, I don't know exactly, on the global shutter sensor at the end. What is the maximum resolution you can achieve with the system in terms of pixels?
Maximum resolution is 2 megapixels. So with a proprietary approach to demosaicing of that pattern, we can arrive at 2 megapixel resolution, which is probably the largest, in terms of, dynamic capture of, as a company that is always like appreciating challenges. We are still, looking into like improving that even further. But currently we are at 2 megapixels.
But you are offering products which have a bigger resolutions, larger resolutions.
Yes, we have also standard structured light approaches and products. That's this family is called Foxy 3D scanner. But those are for static scenes.
Okay.